Today, we are taking step 3 into calculus. Step 1 was limits. The limits were the foundation of everything we do. Step 2 was continuity. And we can't do continuity without limits because the 3 things that have to be equal in order to be continuous are what? Right hand limit, left hand limit,
and f of c.
And f of c, the y value. Okay? So without limits, you can't do continuity. And without continuity, you can't do step 3, which is the derivative. Okay? We are starting to lay the foundation for derivatives today. Okay? So before we do, however, we're going to have to go back to Algebra 1 and Algebra 2 for a little bit. Is that okay with you guys?
Yeah.
I think you would be all right with doing that. So let me sit down.
Can we take these in our spiral?
You can. This first part, yes, you can take this in your spiral. So the first part I'm going to put on the back of the difference quotients worksheet. Okay. I want to review a couple things with you. First one. You can write this on the back of the worksheet you have in front of you, or you can write it in your spiral. It's up to you. Okay. First of all, what is the formula for finding the slope of a line? No, that's not the formula. Okay. Rise over run is one of them, yes. Okay. Another one that I heard somebody say was y what? Over x2 minus x1. And there's a third one that's kind of obscure but needs to be known. Y over change in x. Do y'all remember that one? Delta y over delta x. Okay, that's going to come into play a little bit later. What exactly are this x1 and y1 and x2 and y2? What are they? They're points, aren't they? So we have a point here, say x1 and y1. And we have a point here, x2 and y2. And we're finding the slope of the line that connects them by subtracting the y's and then subtracting the x's, which creates the rise over run, which creates the slope. Okay? Now, do you remember when you first learned this? And I think for some of you, this was kind of complicated and really had a tough time with this because especially when you plot points, you go left and then up, but when you do slope, you go up and then right. You know, it's opposite directions. It's kind of confusing for students. Okay? We're going to take this a step farther today, and we're going to talk about something that you may have heard of before, but you may not have, and it's called average rate of change. And this is a very, very important formula in calculus. Average rate of change. Okay? What have you heard in math so far that is synonymous with rate of change? What's another word for rate of change? Slope. I hope you've heard that slope and rate of change are the same thing. They are. Average rate of change, average slope. So the rate of change formula is very similar to the slope formula. Just uses different letters. And in science, what is another word for rate of change? Velocity. So this formula is for average rate of change or average velocity as well. So I'm going to do this more of a graph like this. So if this is time and this is distance, let's say you're driving to Houston, okay? And you go a distance of 120 miles in 2 hours. Okay, so at time 0, you're still at home. So that point is 0, 0. And 2 hours later, which we're going to say is 2 hours here, you have gone a distance of 120 miles. So this is the point 2, 120. Okay? The slope of that line would tell you how fast you were going on average, right? Okay. How fast would you be going on average? 60 miles an hour. 120 minus 0, 120 over 2 minus 0, which is 2, 60 miles an hour. Now, were you going 60 miles an hour that entire trip? Probably not, especially if you stopped at Buc-ee's along the way, right? Yeah, love Buc-ee's. We had a great conversation about Buc-ee's last period. Okay, so that was your average velocity. But could I be sure that if you told me I left at noon last Saturday and 2 hours later I'd gone 120 miles down the road, could I be sure that exactly at 1 o'clock you were going 60 miles an hour? No. But I could know that on average you were driving about 60 miles an hour, okay? So the formula that we're talking about is talking about averages. And I'm going to draw one more picture over here. Here is A, here is B, because you don't always start at 0, 0. Here is A, let's put B right there. The line that goes through here, we're going to call y equals f of x. Now this is a little bit more challenging. I need to know the coordinates of that point right there. Okay, what is its x coordinate? It's A. I would agree with that. What is its y coordinate in terms of f of x? It is f of A. Think about it. Because isn't that how you find the y coordinate? Don't you plug it into f? Yes. Okay. Now, so then can you now tell me the coordinates of that point? B, comma, f of B. Okay, because I'm kind of getting a little crowded, I'm going to change colors. So, now using the same format as this up here, I want you to write the slope equation using these 4 variables instead of y2, y1, x2, and x1. What would that be? What would I write first? F of B minus f of A. Does that make sense to everybody? y2 minus y1 over B minus A. There it is. Put a big star by that. That is a very, very important formula that you need to memorize for average rate of change and average velocity. It's the same formula. Okay? F of B minus f of A over B minus A. Okay. Now, this is the graph I drew to find the average velocity. Now let me come back here and let's draw a realistic graph here. So at time 0, you were at 0. Here's the time. Here's the distance. And up here at time 2, you were at 120. In reality, would the graph of your trip to Houston, I know this isn't the whole way because Houston's farther than 2 hours, would your graph of your trip to Houston be a straight line? No. No. It could have dips in it. It could go along for a while and then it could flatten out. What happens when you flatten out? You're having lunch. You stopped at Buc-ee's, decided to stop at Buc-ee's and get some beaver nuggets or whatever. And then you decided to go a little bit faster and you took another pit stop and then you went the rest of the way. So that's the reality. Now, is it really straight lines? Well, when you accelerate, it's going to curve a little bit, okay? So, honestly, I could make this thing curve a little bit, and I'm going to for a reason here. Let's make it curve a little, okay? All right? There's a nice little curvy graph, okay? Okay, so now, I already did. Okay, the new thing we're going to start talking about today is what is called instantaneous rate of change. I didn't spell that right, did I? Instantaneous. Instantaneous. That doesn't look right. Let me do it again. Instantaneous. Yeah. Right. You can pretty much deduce what it means. Okay, instantaneous rate of change. That means how fast am I going right there? Whoa. Okay, we don't know what a derivative is yet in this class. Can't go there. Okay? Now, rate of change means slope. So the question is, I want to know the slope right there. But that's a problem. What's the problem with finding the slope right there?
There's a lot of curves.
There's a lot of curving going on. And how many points do you need to find a slope? You need 2. You need 4 coordinates but 2 points. Okay? So, if I wanted to find the slope right there, I'm kind of at a little bit of a problem because I only have 1 point and I need 2 points. Now, let me say this right here as well. The slope of a curve is equal to, just write this down and then I'll explain it. The slope of a line tangent to the curve at a given point. Very important concept you need to understand. So if I'm saying I want to know the slope right there, I'm actually saying I want to know the slope of a line that's tangent to that curve right there. Now, we understand slopes of lines. We've been studying that since Algebra 1, okay? I bet you could estimate the slope of that line. I know you can at least tell me what sign it is. What is the slope of that line's sign going to be? It's definitely positive. I would agree with that. Okay? Now, this is really not a good curve to show it. Let me draw in another one. I thought this would be a good one, but this will work this way. Here's a curve. Okay? Let me pick this point right here. That definitely has a positive slope. Do you see a point on this curve that I just drew that would have a negative slope?
Yes.
Would it be over here?
No.
Here?
Yeah.
Over here? Right there. Right there.
Well, like,
So you're visualizing what the slope would be sign-wise at this point, which is good. You need to be able to do that. But with what we know mathematically, we cannot find the slope right there with only one point. Okay? So what we're going to learn how to do today is do what's called a difference quotient. And a difference quotient is a way to estimate the slope of a curve or to estimate the slope of the tangent line at a certain point. So this is a slope estimator. Okay? So let's go back up here for a minute. I just said this is called a difference quotient. What does the word difference mean in mathematics? What does quotient mean?
multiply.
Not multiply.
Oh,
Divide. Look at this formula right here. Is this formula not just full of dividing and subtracting?
It is.
Yes, it is. This is the difference quotient foundational formula right here. Okay? You are taking the quotient of two things that are subtracted, so that's why it's called a difference quotient. Okay? So I'm done with notes on this page. We're now going to go to the worksheet. So turn this over. I'm going to pull this out because it's got writing on the other side. I want to look first on the right side of this. Okay? Now, for calculus purposes, there are three different types of difference quotients. And over here on the left, they give the three names. There is the forwards difference quotient, which is abbreviated FDQ, the backwards difference quotient, which is abbreviated BDQ, and the symmetric difference quotient, which is abbreviated SDQ. We're going to give you an example of each in terms of a theoretical formula, and then we're going to put, some reality. So let's go to the right first. We have the parabola x squared, something very easy to work with. Well, how would we estimate the instantaneous rate of change or the slope of the curve at 3? So here's what I want you to do. Take your pencil and draw a dot at the point 3, 9 on the curve. It says it wants to find the slope right there. Now, can you tell me what sign it is right there? It is a positive slope. I agree. Now, I want you to put a little arrow and call that x. We are going to do, first of all, an FDQ, a forwards difference quotient. So I want to go forwards a little bit from that point. So if I'm going forwards in x value, would I be going up the curve or down the curve? I would be going up the curve. So go up the curve and just put a little x right there. Okay? The coordinate of that little x is going to be x plus a change in x. X plus delta x. Okay? Every time we are going to write a forwards difference or forwards, backwards, or symmetric difference quotient, the first thing we always do is write the interval on which we're doing this, basically defining A and B. Now, we're going to write this like a domain. When you write a domain down, do you put the smaller number first or the bigger number first? Smaller one. Of these two, which one is smaller? X is. Very good. And then x plus delta x is bigger. So write it in brackets like so. This is your A, this is your B. So we're going to write this problem in terms of the formula we talked about on the back, f of b minus f of a over b minus a. So it's going to be f of b, which is x plus delta x, minus f of a is x, over b, which is x plus delta x, minus a, which is x. Does that make sense to everybody what I just wrote down? F of the b up here minus f of the a over b minus a. Okay? Any questions to this point? Okay, I think maybe if you're a little bit confused but don't want to say anything, let's do one more and see if that unconfuses you. The second one is the BDQ, backwards difference quotient. Okay, so we're going to put another dot at 3, 9, right there. So I want to, and that's x again. I want to go backwards a little bit. So we're going to go backwards a little bit. Okay, we're still going a x backwards. So who knows how we're going to write this down? So it's x what? Minus delta x. Very good.
Wouldn't it still be change in x? Wouldn't it be plus change in x because the change in x is negative already?
But we're talking about what the coordinate would be, the x coordinate would be at that point. It would be, if you went starting at x, you would have to back up delta x to get to that other point.
Right. That's what I'm saying. I mean, if delta x is negative.
Delta x is always positive because it's a distance.
Oh, not as much.
Right. Okay. So how would the interval look this time? Which one of these two do I write first? X minus delta x because it's smaller. And then x is second. Equals fraction bar. F of, which one first? X. Always the second one first. Minus f of x minus delta x over the b, which is x, minus the a, which is x minus delta x. Notice that I'm putting everything in parentheses. Please do the same, because you've got to watch those signs. They can really slip you up. Okay? Now, after doing 2 of these, do you feel a little bit better about how this is fitting together?
Yes.
Yes? Okay. Last is the symmetric difference quotient, SDQ. I want you to put a dot at 3, but make it tiny because we aren't even using it in our quotient. Just a little dot right there. We're going to go a little bit up and a little bit down.
Wow.
Now, the whole width is not delta x. You're still going delta x up and delta x down. Okay? So
it's forwards, backwards, and what changes?
Symmetric. Okay? So the upper x would be x what? Plus delta x. The lower x would be x minus delta x. Are you with me? Write the interval. Which one do I write first? X minus delta x is first. X plus delta x is second. Equals, you write it down. See if you can write it down. And then check with your table to see if you get the same answer. Okay, when you're done, look up here and see if you got what I got right there. Okay. Now, you may just be going through the motions and doing this, but do you understand what's going on? Matt, do you have a question?
They said the second one first.
Yes. The second one, i.e. the larger one first, when you do it here. X plus delta x is larger than x minus delta x. Okay? All right. Questions?
If I watch the video, will it make more sense?
I don't have, this is, if you watch it again, it'll probably make more sense, yes, after we do this. Okay. Is everybody done writing this down? Can I move on to the other side? Okay, slide your paper over. Let's look at this. Okay, I want to talk through where all of this came from, okay? The question states the instantaneous rate of change of the function f of x equals x squared as x equals 3 is estimated below using 3 types of difference quotients and delta x equals 0.1. Now, they're giving us values, and so instead of talking in theory like we did over here, we're going to talk in reality over here, okay? But before we do, I want to back up. I did this last period. I forgot to talk about it. I want you to take a minute, and I want you to talk to your table, and I want you to think about which one of these 3 would be the best estimate of the exact slope through that one dot. Talk about it with your table. Which one do you think is the most accurate? Which one of those 3 do you think is the most accurate? Forwards, backwards, or symmetric? Okay. Would anybody like to volunteer what their table came up with and why? Lex, go.
All right. We chose the symmetric difference quotient.
Okay.
Because basically it gives us an average between x plus delta x and x minus delta x.
Okay.
Which would give us like a more exact point.
Okay. I think that's a valid argument. Okay. Now, does anybody have anything to add to that? Anyone that you think is the bet? Okay. Do the rest of your tables think the symmetric is the most accurate?
Yes.
Okay. I'm not actually going to tell you for sure yet which one it is because I'm going to show, you're actually going to discover it through doing this other side of the paper. Okay? So, keeping that in mind, let's come over here. All right? Now, the forwards says f of this, oh, wait a minute. Where did all these numbers come from? Let's back up for a second. I'm actually going to cover this up with my fingers, and I want to write the interval. I wish they did that, but they didn't do that before.
3.
Okay? If we're going forwards, and we're doing it around 3, would 3 be written first? Let me say it again. If we're going forwards, and the point in question is 3, do you write the 3 first?
Yes.
The answer is yes. 3 goes first. Okay? Look over here if you're not sure. When we wrote forwards, didn't the x go first? Yes. Okay, the second one's supposed to be x plus delta x. So how do you write that number? 3.1, just 3.1. Okay? Now looking at that and looking at this fraction, does this fraction now make sense? Does this fraction now make sense? Shh. F of 3.1 minus f of 3, 3.1 minus 3. Okay, where did these squareds come from? Because the problem initially is x squared. So the problem's saying, oh, we're supposed to square these numbers. So you square them. So 3.1 squared minus 3 squared over this is what they got.
Wait, why are you squaring them?
Because the equation in question is x squared.
Oh.
So f of 3.1 would be 3.1 squared. Because if you go up here and plug in 3.1 for x, you're going to put 3.1 right there. Okay? All right. Cover up the equation here. Let's see if we can write the interval.
2.9.
2.9 goes first, and then 3. Because it's starting at 3 and going back 0.1. So that's 2.9 and 3. Does the first fraction make sense now? It should. F of b minus f of a. Here's the work. Here's the answer. Here is the symmetric. The interval for this one should be 2.9 and 3.1. You basically take these two and drop the 3's. Okay? There's the work for that one. All right, now we're going to do one together, given no information. Is the x the same? Is the delta x the same? Yes. All it's changing is the equation. So what I'm going to do first is write the intervals above each column. And they are going to be the same as they are over here. 3 and 3.1. Here is 2.9 and 3. And this one is 2.9 and 3.1. Okay. So, the first fraction for this one, in terms of f, would it be exactly the same if it was log or if it was x squared? Would I still write f of 3.1 minus f of 3? Yes. So I'm not going to write that again. That's a waste of paper. I am going to write, though, what it is in terms of the function. I'm going to do the second fraction. I'm plugging into log. So it's going to be log of which one do I write first? 3.1 minus log of 3 over 3.1 minus 3. Okay? So now take your calculator. Okay. If you have an 83 calculator, you're going to need to put the top and the bottom in a parentheses. If you have an 84, you can use the fraction bar, alpha y equals, and enter, and just type it in. But make sure you close the parentheses after the 3.1. Log of 3.1 minus log of 3, 3.1 minus 3. And we're going to write out 0.142 dot dot dot. Calculus is 3 or more decimal places, rounded or truncated. If you've been in pre-AP all along, I think they've been teaching you ever since geometry, 3 decimal places, 3 decimal places. This is why, because that's what calculus is, 3 decimal places minimum. You can go more than 3, but 3 is the minimum. Okay? Are we good with that? Now, compared to the exact answer that they give you, small, too small. Okay? Do the second one. How would this be? Log of which one? 3 of 2.9 over 3 minus 2.9. Okay. You should get 0.147 dot dot dot, which is a little too big. Okay. I want you to do the last one with your table. Now I went out 4 decimal places on the last one just to show exactly how close it was to the exact answer. So is our theory correct? Is symmetric the best? Yeah. Yes, it is. Okay? Now, we are not going to do ln because it's just like the log. I would like you to do with your table right now the e to the x. Set up the fractions, do the math, make sure you're typing it in correctly. It's still the same intervals as it is up here.
Does it get much harder than this?
No, this is it.
This is it.
This is it. Climbs very fast. Okay, we'll give you about 1 more minute and then I'm going to talk about a couple of these. And I want to record it so that those who didn't see this first period have an access to it, or who are absent today. My debaters. Okay, anybody need more time? Okay, go ahead and take this worksheet you just got right here. Okay, right here. We're actually going to do numbers 1 and 2 together because we talked about 1 in class. I want to make sure you know the answer to this question because this is basically what I want you to leave class with today. Who can tell me, and I've already alluded to it, what's a difference quotient for?
For finding a slope of a curve.
Okay, I'm hearing lots of little pieces. I'd like you to raise your hand, please, and tell me what you want to say.
Oh, now the question.
Okay, Gavin, I'm going to start with you, and then I'm going to come over there. Go for it. Finding the slope at a point. That's good. Let's add to that. Let's make it a little bit.
Finding the slope of a curve.
Okay.
That's what I said.
Okay.
Go home.
Okay. I still want to add one more little thing to that. Okay. Are we finding the exact slope of a curve?
No.
We are finding an estimate or approximation. So the purpose of a difference quotient right here, for finding the estimate or the approximation to the slope of a curve at a given point. I'll give you a second to write that down. Method to approximate the slope of a curve at a given point. The method to approximate the slope of a curve at a given point. Okay. Now, I know several of you guys in here are what I would call it minimalists. Minimalist meaning you want to write down in mathematics as little as possible. Now, some of you write down as little as possible because you don't really know what to write down. Some of you guys write me novels, I know that, and that's fine. But let's talk about what I want on these homework problems. So I want to do number 2 with you. Find an approximation to the slope of the tangent line. That's why I just defined a difference quotient is. X equals 2, that's important. To the graph of this function using a forwards difference quotient with this delta x. Okay, so F, D, Q equals. Before we can do this, you've got to write the interval down because our interval is now different from what we did on the notes. Okay, if I'm going forwards, what number do I write first? I write 2. 2.01. Be careful with your decimals. Okay? Now, the first step on all of these is going to be writing it in terms of F only. I want F of, which one do I write first?
2.01.
2.01 minus F of 2, but the bottom does not get F's. It's just 2.01 minus 2. That must be first on every problem. Every single problem. Then, the next step is to do the math. Okay? So, you have a couple of options. The first option is to, if F of 2.01 means to plug that into here, I could type 3 parentheses 2.01 parentheses squared minus 2 parentheses, 2.01. But there's a faster way. Would you like me to show you the faster way? Yes. I had a feeling you would. Okay? I want you to go to y equals and I want you to type in the function. I'll wait for you because it's already in my calculator. Okay? It was there from last period. Type that into y equals and you can do this every time. Then I want you to do zoom 4. Remember I told you zoom 4 is the one you want to choose first? See if you see something. I see something. Okay? Now, this means, F of 2.01 means I want to find the y value of 2.01. So, to find a y value, the quickest way is to push the trace key and type in what you want, 2.01. And it'll show it at the bottom of the screen right there. Okay. Never, 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 never round before the end of the problem. So I want all of those decimals. I don't care how many there are. 8.1003. Okay?
You gotta do that every time.
Every time. Minus. Now, F of 2, that just means I want the y value at 2. So I'm going to push trace again. Oh, it just popped up there. Well, that was kind of interesting. 2, 8. So 8 goes next. Over. 2.01 minus 2. Okay, so step 1, write it with F's. Step 2, give me the numbers. Step 3, just give me the answer. So now I go to the home screen, type this in. Alpha, I did it again, alpha y equals and enter. 8.1003 minus 8 over 2.01 minus 2. And there it is. 10.03, and that's the answer. Okay? All right, let me say one more thing before I pack you in, because I know the bell's about to ring. Look at number 6 for a minute. Okay, I had a student ask me a question last period, and somebody in here might be thinking about it. Why would you even do a forwards and a backwards if symmetric is always the best? Here is why. Okay, look at number 6. Okay, actually for a second, look at number 5 first. Number 5 says find all three. The one we just did says find forward. They'll either tell you what to do, or there's only one that you can do. Look at the data on number 6. It says find an approximation, which means only one, to the slope of the tangent line at 4. Look at what they give you. There's only one of them that you can do. Which one is it? Backwards. Do you all see that?
Yes.
The only one I can do is backwards. Now, does it matter how far I go back?
So for 5, we can do all 3.
Yes, you're supposed to do all three. Okay, which one would give you the best estimate going backwards? 3.9 would give you the best. That's the one I want. You always go as close as you can. 3.4 to 3.7 would be an estimate, but it's not the best estimate.